Okay, now we continue with the cyanidation of gold, and we now know the proposed theories that have been suggested in how the reaction for gold dissolution occurs. It is on this background that you also begin to see that for systems, certain systems, to enhance or increase their gold dissolution activities, you find that they begin to add other reagents such as your hydrogen peroxide and such as even your nitrates further hydrogen peroxide, as we saw it, your nitrates to increase the oxygen that is available for the system. Some do oxygen or just even purging, just to increase the rate of your cyanidation of gold. It is because of these certain stages of these steps of these reactions that we have seen, according to these theories, that it is believed that now if you add, for example, your peroxide, then your gold dissolution can actually be catalyzed. Okay, what are the factors that affect gold leaching? Okay, now there are several factors that affect your gold leaching. So here are some of them. Particle size, your residence time, free cyanide concentration, dissolved oxygen, slurry pH, and even your foreign ions, actual or also even your temperature. Okay, so here we talk of effect of particle size on um, on cyanidation. Now, you remember we talked of mineral processing in our first lecture, and we said mineral processing involves, first of all, you've got an ore which has got your particles here that you want, okay? And then we said you do the process of comminution, and the process of comminution, you end up with your wanted, unwanted, wanted particles, maybe unwanted, maybe wanted particles, unwanted, and also maybe your unwanted particles. And then we said we now do first of all, this is liberation, and then we now do separation. As we do separation, we now have your wanted materials on their own, and then we have got your unwanted materials on their own. Okay, now the particle size of this wanted material, the particle size of this metal value of choice that has been, in this case, this is now a concentrate. Its particle size heavily affects the process of dissolution. For example, here, if your particle size maybe is on this region A here, close to around 2.5%, 2.5 millimeter, maybe 20% passing 2.5 millimeter. So in this case, you're having a very coarse material, and it will be very difficult, or it will take very long for the cyanidation process to occur. However, when you begin to reduce the size, when you begin to further reduce the size, you realize that your rate of dissolution or your rate of cyanidation is found to go higher and higher as you increase your the size of your as you decrease the particle size of your concentrate or of your mineral of choice. Okay, so it is very important to note that particle size affects the rate of cyanidation. So this is the particle size effect is based on the shrinking core model. Okay, so the shrinking core model simply tells us that this is your unleashed ore, okay, and this is your bulk solution, okay, and in the bulk solution you have got your lixiviant coming into contact with the unleashed ore, okay, and dissolving the metal out, okay. So if this process continues to happen, if this process continues to happen, if the your lixiviant continues to get into touch with the unleashed ore, it will then form, it will then as the process continues, you can see that your core continues to shrink. This is the distance that, in this case, that has actually been dissolved. Okay, so if your ore is very thick, it becomes actually very difficult for this lixiviant to reach the unleashed ore, and therefore your rate of leaching is actually very slow. Okay, And also, even if you this is your particle size like this, and maybe it is still covered in gangue, and here is the particle of choice, or the wanted mineral of choice. It will take a very long time until this core shrinks for your lixiviant to eventually reach this portion of mineral. So particle size plays a very important role in cyanidation. This is why your gold must actually be in fine particulate form when you go for the cyanidation process. So ideally, most plants use a size reduction of up to 80% passing 75 microns. That's usually the real rule of thumb in our gold processing. Although other plants can go several stages, several microns down, or maybe 100 here microns, depending on the nature of the nature of their ores. Okay, but ideally 80% passing 75 microns is the conventional or the typical um, parameter that is used in gold cyanidation. Okay, so as we said, if the particle is too large, then total leaching is very difficult, and actually your residence time in the tanks will actually be very, very high. And you, if you have got very high residence time, it might not be profitable, and at times you need to fast track the process, and hence you find that you to lose your gold to the tailings, which is very, very unwanted and very costly for them for the process. Okay, so under ideal conditions with respect to aeration and agitation, well, the maximum rate of dissolution of gold, although this may vary a little bit, has been determined to 3.25 milligrams per centimeter per hour. Okay, which is this is actually equal to 1.6 microns penetration on each side if you are considering a 1 centimeter flat particle of gold. Okay, so instead of taking a very large particle for your leaching process, um, we said it's better to take a very small particles of your of your of your of your concentrate to the of your ore to the leaching process. So what do you do with these large sized gold particles? If they are free, they're coarse gold particles, then you need to remove them using your Nelson concentrator or your Falcon concentrator. Okay, so when you include a Falcon concentrator or a Nelson concentrator before leaching, you completely take or remove these coarse particles, and then you simply take these very fine particles, 85 80% passing 75 microns. Those are the ones that you now take to the cyanidation process, and they can be leached now in an economically acceptable time. Your residence time, first of all, is low, then the consumption of your reagents is also reduced significantly, hence the need to only take these finely sized particles for the process of cyanidation. Okay. So here this is a quiz for you to answer, for you to try and solve and see what's going on. You've got a flat piece of gold with an area of 1 centimeter squared. We have talked about the maximum rate of dissolution, and now if the gold piece is 34 microns thickness, what is the total time expected to dissolve this piece of gold? Please just attempt this piece, okay? All right. Right. So, um, what are these factors? What's the other factor that affects the rate of cyanidation? Uh, one of these is actually free cyanide. Okay. So according to this Elsner's equation, you can see here, this is your cyanide, and definitely when you increase your cyanide, should be your Le Chatelier principle, something like that. You drive the equation further to the right. Okay. Um, so it means that more gold is actually leached when there is more cyanide. Okay. So, however, you just don't increase the cyanide because you want more gold. You have to do it in an economical method so that you have uh, the cyanide that you want, which leaches your gold in a specific amount of time and also at a specific amount of concentration. Okay. Okay, so here we can see according to this study that was done, so we are increasing on the x-axis is your time, and then on the y-axis is your gold recovery. Okay, and then your square represents 0.5% cyanide concentration, and then your circle 0.15% of your cyanide, and then the black circle 0.25% of your cyanide. We can definitely see that at let's say at 5 hours here, the uh, the gold recovery for your 0.5% potassium, 0.5% cyanide is approximately maybe 65 or something percent. And at the same time here, the gold recovery for your 0.15% maybe is around 75%. And then also at the same time here, at when you're using 0.25% here, you can see that your gold recovery is actually maybe around 95%. Okay, but we said we need to take care of the economics. So when you increase the cyanide concentration, definitely your recovery increases. However, your costs also increase, which is you don't want this, but also your time of leaching or your residence time goes down. So you need to, and the opposite is actually true. So you need to balance your recoveries and your residence time in order for you to have an optimum cost and also an optimum concentration of the cyanide to add, depending on the nature of the ore. Okay, so you can also have what is intensive cyanidation. Okay, um, intensive cyanidation is mostly applied in the treatment of gold mills gravity concentrates. Okay, so one of these examples is the acacia technology that is practiced at Mazoe mine. Okay, so generally, we all know that amalgamation has been the conventional method of treating your gravity concentrates, and because it is actually very cheap, actually, and very easy to do, you simply put in your gold, and your mercury takes care of your gold, and then you simply burn off or you remove the amalgam, and you remain with your gold. So it has been a very easy process, and it's actually been very useful for the. However, because of mercury, and we all know about the Minamata Convention, which Zimbabwe is actually part of signatory and also ratified this convention on the eventual elimination of the use of mercury. Now we are at the ratification stage, so we are doing what is called safe handling, safe usage of our mercury. But at some point in the future, we are totally going to eradicate the use of mercury. Why? Because of the concerns of the environmental aspects that it caused. Okay, so we are now, instead of using mercury, we simply use intensive cyanidation process. Okay, so in the intensive cyanidation process, oxygen is very important. Usually, pure air is actually used to increase the significant rate to increase the dissolution of gold. Okay, so in intensive leaching, so you find that your dissolved oxygen, um, there's a high significant dissolved oxygen in the system, and also a high cyanide concentration than in the normal leaching. Hence the name intensive cyanidation. Okay, right. Then we also have got the effect of dissolved oxygen. Okay, So again, as we see here, increasing dissolved oxygen pushes your further reaction to the right, right. Um, Now, um, although other oxidizing agents such as your peroxides, such as your permanganate, chlorine have been used, adequate aeration actually, if there's adequate aeration, you can actually even result in a very good dissolution of your gold just for the sake of reducing cost. So you need to strike a balance. You find that if you provide adequate aeration, there might actually be no need for further oxidizing agents that people use in the times, even your hydrogen peroxide. If you provide good aeration and you simply increase your residence time to acceptable levels, you can actually continue the process of your dissolution of coal. However, as said in this reaction, your oxygen definitely increases the rate of your dissolution of coal. So amount of dissolved oxygen in a system depends on the four parameters, okay? First of all, there are your altitude, your temperature, your agitation, and then the ionic strength of the solution. So when you alter these parameters, you can also alter the amount of dissolved oxygen that is available in the system. Okay. So this is also another experiment that has been done here on the this is your time on the x-axis and gold recovery on the y-axis. So let's look at 26, maybe 3.5 and 1.0. So we look at the blank circle, and uh, the dark, the dark square, and then also the dark circle. We can see here that at a time of okay. So here we can see here. Let's look at this uh, blank circle 1.0, and then also this dark square 3.5, and also this dark circle at 26 milligrams per liter as your concentration of coal. Now, if we take time at around 5 hours here, we can see that at your 1.0 milligrams, you've got about 60% recovery. How about at your 3.5 milligrams, your square, you have got here maybe around 80% plus 80% recovery. Okay, then you have got here your dark circle. The dark circle, maybe this is the graph here. You can see that you have got a very high rate, which is maybe around 95% um, dissolution rate, gold recovery. Okay, so it simply shows that when you increase the rate of when you increase the concentration of your dissolved oxygen, then definitely a gold recovery will also increase. So from the dynamics here, if you increase rate of oxygen, dissolved oxygen, your recovery also goes up. But because pure oxygen is expensive, your cost will also go up, and then your residence time or your time of processing will go down. Okay, so you need again to say balance these parameters so that you still remain in an economical position. Remember, whatever we do as metallurgists must also be profitable to make money. You cannot be a metallurgist who enjoys leaching and having high recoveries, having short periods of time, and yet you are not making any money. You need to do your recoveries and your time and optimize them so that your operations is also profitable.